Let's do it. Oh, good. So our speaker today is Timur Dogan. He's an assistant professor from the Department of Architecture. So we sort of work, know the people from AAP, right? So over a long time. So Timur, I would say he's the most engineering focused architect I haven't seen on campus. Or you will see, right? So he's working on. He's in a nice position, right, to conduct the architect practice with, I would say, engineering and simulations, right? So and hopefully you'll enjoy. So Timur, before he has his current position at Cornell, he was MIT Presidential Fellowship. Might be it's a very prestigious fellowship at MIT. He graduated. He did a postdoc with MIT Building Technology, which I recently visited. Very impressive. And he also got a master's degree from Howard Graduate School of Design. And his architecture degree from Technical University of Darmstadt. I said that's in Germany.
Yeah.
So you got your master's degree at Howard and then went back to Germany, guys?
No, first Germany and then.
For Germany and then Howard. Okay.
Postgraduate stuff.
Postgraduate.
Howard and then.
And he currently also he was also a German national. He was also a fellow of German National Academy Academic Foundation. So we look forward. Also, I think Timur also worked with engineering students.
Yes.
Right. So
in fact, there's 3 students I know. I thought I would not know anyone here, which is great.
Cool. So let's have a word of welcome of Professor.
Thank you, Max. For the introduction, and thanks for having me here. It's a great pleasure to speak to you engineering students today, because I think what we need is much more this cross-disciplinary collaboration. And you'll see, maybe you'll find a place where you fit in as a researcher in the things that I'll be showing you today. So I'm talking today about architecture, and I'm talking about architectural design, and I'm talking about its relationship to environment, to the environment and environmental performance, sustainability, and per se, right? So why should we care? Why is the built environment so important when it comes to sustainability? It's we are looking at around 2 billion new urban dwellers by 2050. So people are, A, population is growing, and B, people are moving towards cities. That means that we'll have to build an equivalent of 250 times the New York City by then, which is, worrisome because the built environment is associated, or 33% of the greenhouse gas emissions are attributed to buildings, right? So this is the biggest contributor, the single biggest contributor in this whole domain, are buildings. And if we break this out even more, then we look at, this is the US energy consumption data from 2007, so I think still okay, probably there's updated data available to you. Now, buildings are consuming 42% of the operational energy. Building the buildings costs another 6% of the energy demand annually, right? So, and if you look at transportation, cars with 16%, before you buy a Prius, maybe fix your house, right? That's probably much more impactful than looking at the transportation sector or industry sector alone, right? And that's why we really want to talk about these things. The other issue is livability. The minute we have many urban dwellers living in high-density urban environments, this is a picture of Hong Kong, where we really have to kind of question, is this the right way to do it? Do people have the right amount of access to direct sunlight? We have pollution issues. This is a picture of LA during rush hour, probably. Right? And then solar access is another kind of qualitative parameter that we want to look at. And then on top of that, there's a resiliency issue. Most of the urban centers are built near coastlines, and those are all going to be affected by climate change and sea level rise, right? So those are the things that we really need to kind of get right when we deal with the urban environment and the built environment and as we move forward. So I kind of painted a very negative picture at this point, but I think it's also a great opportunity. It's a challenge for us as architects and engineers to kind of make this better, right? So the fact that we have to build a lot of new buildings gives us the opportunity to kind of turn this around, to work with these and solve these problems that I have just mentioned, right? And what I'm interested in is this like true paradigm shift in sustainable architecture. What we often see in current practice is that you start with an idea that may or may not be so good from the start, and then as an afterthought you bring in sustainability, and then you add solar panels, and then in this case hilarious solar wind turbines. I don't even know what that is, but you know, there's a lot of this greenwashing going on in practice, and that's really not what we are interested in at AAP. And I always show this picture of a car where, you know, the performance and the design really come together. They're engineered and designed at the same time in a highly integrated way, where, you know, you see kind of a symbiotic relationship between the aesthetics of the car and its kind of performance, in this case the drag coefficient, which was of interest here, right? So, and we are interested in kind of something very similar to this design process of a car, but obviously with buildings. And what are the ingredients of such a design process, right? So we use a lot of simulation tools, and we actually have to develop our own tools because the tools are not there. They're not really doing what we need them to do. And then this is really kind of the key component here, is that we develop algorithms and interfaces that are fast, quick, responsive, immersive, right? That allow people to kind of really understand the problems. It's a highly complex situation that you're dealing with as a designer, and you have to deal with so many different parameters. So you can't really add an extra layer and a really complex one if you don't have smooth interfaces and fast simulations and fast feedback turnarounds, right? And then the design integration only kind of is then really natural as a fact, where you use it in class. We try to drive this through teaching and you know, developing generative design workflows where you can embed the analysis. I'll show some examples later. And the other third part that's really important is that we kind of think across scales, like from the building to the room to the systems on the facade and the components of a building, and you know, neighborhood scales even. And we think that we have to think across disciplines, right? This is not something that an architect alone can solve. It's usually a team of people that have very different skill sets, right? So, and you'll see how the composition of the lab is something that that is quite interesting. So I briefly want to kind of touch the teaching part here, because the classes that I'm teaching are core curriculum classes for architects, right? So for engineers, they may be a little you know, simplistic in one way on the engineering side, but and then overly challenging on the design side, right? So, but we had a couple of engineers taking these classes, and they've usually thrived in these classes as well. Like, and since you're working in teams, it's really an interesting thing to look at. So there's, you know, basic principles in sustainable design. Building systems are a more advanced class. Then we teach design studios that usually deal with urban situations and so forth, right? On top of that, we have these kind of open lectures that we organized a couple of times, and then this one in the middle was organized together with systems engineering. So there's a lot of interesting things going on if you want to kind of get to know these things. So what we do is we start very analog physical models to kind of understand how light, for example, enters a space. It's usually a very fun exercise where you start taking pictures of the physical models inside of, but then you use this photograph to kind of talk qualitatively about the light, but we also want to teach how to quantify these things. So in this case, what you're seeing here is an HDR photography that has been calibrated with luminance measurements in the model, and now you can basically tell the brightness levels at each surface and kind of quantitatively kind of prove the concept or the design idea, whether it's working or not. And then moving kind of from these kind of analog explorations that we do in the classes into simulations. So the students get exposed to this really fast. Energy simulations, we tend to play a game where they compete for the kind of lowest energy demand in a building task. So the last series was a net zero office tower where they had to really bring down the energy demand. So the goal was already set in the competition in a way, right? So we do form finding exercises how do you collect solar energy the most efficient way, and then how do you fit the program in there. And we look at the facades in great detail, and then end the whole thing with a small exhibition on the models that they have produced. But and this is kind of the takeaway from this simulation game approach that I started with my PhD advisor actually at MIT back then. And we played this game, and what we showed is that architects without any special training with this game can significantly reduce the energy demand of a building, right? So you see up here, is there a pointer with this? Oh, maybe not. Okay, so in the top graph you see kind of the iterations that groups did, and you can see how they were able to push down the energy demand over several iterations. But the most encouraging fact was that the students really loved the way they worked with energy modeling at that point, right? So it was a really engaging exercise. Now, this way of teaching these topics only works with the research that we're doing in the lab. And the lab is a very interdisciplinary team. And you're seeing a few of them here. I think Isha, who's sitting here in the front, was missing on that day. And Zach recently joined. Thomas, who's sitting in the back over there, has worked in the lab in the past. And what we are really doing is kind of pushing these boundaries forward, where like how can we embed these performance feedback loops into the design process, right? And what we think is really, the way we think about our research is that it's somewhere in between design or architectural design, engineering, but also computer science, because we have a lot of computational problems to deal with in our daily work. And so the research across scales is important to us. We really look at anything from the component scale to the neighborhood scale, and anything that has to do with operational energy in buildings, daylighting in buildings, natural ventilation of buildings, for example, comfort inside and outside. Outdoor comfort is a big topic kind of that's growing recently as a research field. Life cycle analysis, but also resiliency. So what happens if a building or if there's a power failure in the grid, buildings without any electricity, can they survive? Do they maintain temperatures that are survivable or comfortable, and so forth, right? And I brought you a couple of projects today to talk about them in more detail. We started a little late, so maybe I have to rush through a couple of them, but we should be fine. Out of these kind of three different scales, from the component to the building to the neighborhood. And I want to start with this one. This is it was a fun exercise that we did at one point as an aftermath, basically, of a project in practice we worked with. So Light Shelf 2.0. So this was a school design that I was involved in Ergolding, Munich. Near Munich, it's in Bavaria, Germany, where the architects, they had this idea, okay, we orient all the classrooms to the north, then we don't have to deal with glare. And the issue with that was really that this is the kind of the conceptual sketch or the diagram, is that you have a classroom and they're facing north, they don't have a glare problem, they don't have an overheating problem, and they have fairly uniform lighting coming on from one side. But the classrooms are so deep that you always get this light asymmetry, and you have to kind of have the electric lighting turned on during the day. And that we thought wasn't a very efficient way of dealing with the situation if this was going to be a very sustainable building. So the idea was to introduce a light redirection system on the southern facade to illuminate this kind of the south-facing side, the interior edge of the classrooms. And okay, so this unfortunately is not an animation anymore, but you can really kind of quickly see the idea was to buy off-the-shelf lamella shading systems and then use those to track the sun elevation and to redirect the light. What you see in the animation now is obviously you can tell that this is not a smart idea, right? So what happens is the redirection is really kind of out of control, right? So this is kind of the redirected sunlight, and in the animation this would just wander around the whole space, which creates a lot of issues. It's not very effective. You don't get the light where it needs to go. Plus, it can lead to glare issues where you kind of start blinding people walking through the hallway. Right? So this kind of idea was ditched really quickly. And then, in the academic context, we said, okay, let's think about this one more time. Now we have the freedom and the time no rush deadlines and so forth. Can we do a 2-axis redirection system that doesn't have these issues? And so what we then started with is simple idea, right? So what's the concept? How do we do this? Then we use simulations to test whether this idea is actually any good. Does it have any impact? Is it meaningful enough to kind of justify the effort? And then we move into kind of prototyping, rapid prototyping with these simple Arduino or whatever's out there, Raspberry Pis to play with to control kind of a dynamic facade systems, right? And the simulation setup at the time was quite sophisticated, even though it's such a simple process. Doing kind of dynamic facade systems, simulating dynamic facade systems over the course of an entire year in hourly steps is quite heavy computationally. So we used the cloud, which then makes computationally heavy very expensive. But okay, so and then this is another animation that basically shows how this kind of the mirror shelf rotates, and the light constantly stays where you want to have it. And it's really interesting. You can kind of point it and configure the system to kind of keep it constant in one place. And then you see here the difference without a system and down below, and with the system up above. So you can kind of really illuminate the backside of this room. So this sounded interesting, but then we wanted to know, seemed to work kind of geometrically, but we wanted to know how effective is that over the course of the year. So we tested different systems. So this is kind of the typical office facade that you would see in the US with a blind system for glare control. Then something that maybe was really popular in the 80s, where you had like a light shelf and a clear story. So you basically move the blinds down a little bit, and then you have your shelf, which reflects light deeper into the space, and then our dynamic system, which is kind of the reinvention of the light shelf, the static light shelf. And you see that this really kind of pushes the lighting levels in the back. And we tested in different climates with different, different sun angles that we were to expect, low and high sun angles, and then clear skies versus cloudy skies and so forth. And over the course of the year, you see. So now I think this is the Phoenix example. It's quite good. You see how this works really well for low sun angles, but then when the sun is high in the summertime, the effectiveness is not so good anymore. So it's not a perfect system, but it was an interior installed system. So that was it was expected to happen, that it would the building floor slabs would start shading it and at summertime. But nevertheless, even without this being perfect, you could reduce the energy demand for lighting. And we assumed LED lighting, so very low lighting power density. You could kind of push down the demand by a factor of 16% to even 35%, which is still significant in addition to the kind of the aesthetic qualities of kind of the daylight being redirected into the space. And this is kind of the prototype that we then built. Now this was kind of the facade component, right? That's interesting to look at. Now let's kind of jump into the building scale. Building scale, we have to deal with obviously a lot more kind of holistic analyses, and this is from a lab building that I was commissioned in Turkey. The design, so it's like a multidisciplinary lab. That in Kayseri, that's a town kind of in the middle, central Anatolia in Turkey, where it's really hot and arid in the summer and super cold in the winter. So how do you kind of deal with this? What's the main idea here when you're talking about design ideas? So the main idea really was the central atrium, that you could use for circulation, but you could also use it for communication. So you kind of bump into people from different disciplines, kind of occasionally. And you could use this central atrium as a screening place for lectures and events and so forth. And then also combine that with the food and have a cafe here, right? So to kind of really foster this communication between the different disciplines that were housed in this lab. And this is how, a rendering of the space, how I envisioned it kind of like architecturally at that time. But the atrium also had to have, was supposed to have like environmental benefits, right? So one thing is the daylighting. Obviously, if you have very deep labs, now you can kind of bring daylight in from two sides into the lab, which is quite beneficial. And then the other aspect was that this atrium space could be used for natural ventilation for the non-kind of mechanically ventilated spaces such as the labs and so forth, right? So the question really was, can we, as architects or as designers, can we quantify these things and tell our client whether that's worth it, right? So what you would need there is an energy model, right? So you need a whole building energy model to kind of justify that, test whether the natural ventilation is effective, whether the daylighting is effective. At the time when I started my PhD, energy modeling looked like this, right? So you had a spreadsheet, and you had to enter X, Y, Z coordinates for every wall, and then enter all the systems. So it's kind of like a very, very rudimentary process, which is okay if you're testing boxes, but not if you're testing entire buildings, right? So this wasn't really very feasible to use in a design process. So I started kind of building my own tools during the PhD even. So we developed this tool called ArcSim, which interfaces with Energy Plus and Transys, which are the common building energy modeling simulation engines. But it's embedded within Rhino, which is a CAD modeling tool that designers and architects use extensively, right? So what it really does, it takes all of the energy modeling parameters and the geometry from Rhino, merges that, and then outputs Energy Plus simulations or Transys simulations. Which, and then the nice thing there is that this is a fully automated loop, right? So then you just bring the results back into the design environment. And at the time, this was unheard of, right? So this is the typical setup. This is your CAD modeling interface. You kind of try and you play and design with your geometry, and then you have a simulation environment in Grasshopper, which is a visual scripting environment. So it gives you the full flexibility. It's like ease of use, few clicks and you run a simulation, but you can also script things and you can do parametric runs and so forth, right? So this allows us to do fully parametric energy models, and by parametric I mean not just the set point on the HVAC system is parametric, but everything, right? The size of the windows, the spacing, the depth of the floor plans, everything is parametric. So the entire building is basically built up of 5 points, and then if you pull these points, everything updates automatically, right? So this is how we kind of looked at the building to kind of test certain things. Now, results that kind of came out of these simulations looked, for example, like this. If you had the question, so how open can the roof be of the atrium? What's the right opening ratio there? And if you just look at daylighting, it's a no-brainer, right? So the more open it is, the more light you get in. But the minute you start looking at the thermal performance of the atrium, and if you said this thing has to be naturally ventilated, then you're hitting limits, right? So you have to be cautious there. How you cannot open it all the time, or you have to have dynamic shading systems on top and simulate them, right? So I don't want to go into too much detail here. You see the different variants of opening ratios in the colored graphs, and up here you see the heating demand, the heating load of the atrium space, and down here you see hours of overheating, right? So we check whether the temperature is higher than 28 degrees Celsius and when it's naturally ventilated, right? So and you see the big opening ratios, and here we see different design interventions like adding shading, like different glazing systems and ventilation strategies and so forth. You see that this large opening ratio is never really feasible when you claim that this is a naturally ventilated space. That's quite interesting to know as an architect during the design process. And the other thing is really then the floor plan layout that we used we used these energy simulations, and lab buildings have extremely high ventilation rates, obviously, for safety reasons. So just the sizing and the layout of these labs has a huge impact on energy demand, right? So just redoing the floor plan and sizing these labs so that only the spaces that actually have this requirement to ventilate with these high air change rates saved us in the design process around 20 to 30% in energy, right? This is something that engineers can't do. You can't, as an engineer, you can't go in and change the floor plan. Architects can do that, but they don't know how to do the energy modeling usually. So this is something that is really just left on the table in current design processes, right? This optimization potential is not even recognized in current practice, right? That's why we think it's really important that there's this highly integrative design process. And so, okay, I don't know if I can do this in 10 minutes, but I'll try. So we have the net zero. The other scale that I talked about is the urban scale. And the urban scale really is the most challenging one, because now we're not just dealing with one building, but we're dealing with hundreds of buildings. And oftentimes we don't even know what exactly those buildings are, right? So you get like these models that are just volumes, and maybe you know kind of what the zoning is and the programmatic uses in these buildings. And now, the goal was net zero. We need a net zero master plan, right? And this is a project that I did together with Transolar and a German urban design firm called Fink & Joche. And this obviously was in China. Nowhere else are cities built from scratch, right? So we started and said, okay, so how do we approach this? At the time, this was kind of for Transolar, one of the first projects at this kind of scale, right, at the urban scale. So we kind of had to develop our own strategy of how we model this and how we test the performance and optimize and so forth. So we started as, okay, we have a massing model, right? This is the first thing that the designers come up with, the volumes, the densities that people, that the designers envisioned there. And also the program allocation is kind of part of this, right? So we know this is residential, this is commercial, and this is going to be office and so forth. So what we said is in this phase, the urban form really influences two things the most, and it's the daylight availability in the buildings, and it's the natural ventilation potential, right? So we need good ways to test this, and in this phase. And then in the next phase, we move forward and we look at loads. We look at energy loads and how can we reduce those. And those are more like material choice, constructions, and so forth, right? So this is what we then did here. We get load profiles, and then the next step we look at energy efficient systems, right? So how can we serve this load? How can we provide the cooling and the heating in a sustainable way? And you look at HVAC systems, but you also look at cogen plants and energy distribution networks and so forth. And then what's left, you have to offset with on-site renewable, otherwise you can't claim it's net zero carbon, right? So at the time, what was done in urban design was kind of these shadow studies, and this also is an animation, right? Where you kind of look at when do the buildings overshadow other buildings, right? That was kind of the gold standard at the time in urban design. But really what we wanted to know is not just that. We also wanted to kind of understand the potential on the inside. So how can we look at the daylight distribution inside of these buildings, or at least quantify the maximum potential that they have, because we don't know the exact facade layouts and designs, right? So these daylight simulations, though, are not really feasible at the urban scale at all, right? So takes around half an hour for a single building or room, and then if you scale that up into hundreds of buildings, then that's really not something that you can do, right? So and then this is something that again where we needed new algorithms, new tools to kind of get this interior daylight analysis. This usually ray tracing based. What if we had like a simple impulse response function that would tell us how the light distribution works on the inside? And then just do the ray tracing on the exterior. Just by doing that, you save, or you 55 times faster, or up to 55 times faster than the typical daylight simulations. And you get the same resolution of data and within a 7% or 10-ish percent accuracy bound, right? And this was something that I also developed during the master thesis daylight simulation program that now all of a sudden allows you to do these kind of studies, right? So you have different urban typologies and you scale them up to an absurd level and you look at the daylight performance. And these things are not on the open field. They always have themselves as context, right? So they are surrounded by themselves or clones of themselves. and they start shading each other and so forth. So what are density limits, right? So this is a really interesting question to ask. If you're a developer, you just see dollar signs when I say this. So we looked at these different design variants, and up here you see the daylight availability as the higher the number, the better. Bear with me here. The typical daylight performance metric, and then down here you see the density measured in floor area ratio. Again, this is the amount of floor area over the lot size that you can build there. And usually, like high density urban environments, Manhattan has regions where it's around 10, FAR 10. And if you say, okay, if this is then the threshold, the 45% daylight availability, if you now look at different design variants, you see they're all performing very differently, right? And there's one that just goes on and on and on until it hits this threshold. So you can double the density without significantly tampering with the daylight availability. And those kinds of things, it's a one-dimensional analysis, right? It's just looking at daylight. There's all kinds of problems with this one design variant here, right? Architectural problems, but also on the energy side, maybe problems, right? But just showing this, I think, is very interesting. If you did this analysis in a much more sophisticated way, you can really kind of show how this unlocks value, right? If you can build twice as much with the same quality, then that means you can, your buildings are going to be twice as valuable as you move forward. So this is quite interesting kind of from a developer standpoint and from this master planning standpoint as well. So how do you actually craft the form so that it doesn't tamper with these potentials, right? So this is daylighting. Now let's talk a bit about energy. So what's typically done at these scales is that you have a massing model, and from that massing model you extract archetypical buildings. So this is my typical office building, and you model that in great detail, and then you just scale your results accordingly, right? So you just extrapolate, but you're kind of leaving a lot of this is a very crude simplification geometrically. This is the contextual shading and so forth. It's not something that you really can take into account. And on the other hand, this is also not a fast process, right? Building these archetypes is challenging, and then you still have to deal with a complex building energy model. So what we did in this project was we said, okay, let's go even one step further, and we just look at typical rooms. And then these typical room distributions we kind of separate into different categories, like unshaded, mildly shaded, heavily shaded, and then different program types, right? And then we use that to extrapolate. But again, you make an error there, right? So you're making a simplification there. So the results that we were able to get, this is our master plan, the typical zoning plan that you would see, and then you see, different variants of, different construction standards and qualities that we assumed. So this is kind of our base case, so our mid-tier and our kind of maximum that we thought was feasible, and then you can kind of give a recommendation saying, okay, so if you invest this much, you get the biggest bang for the buck, and then if you want to go even more radical, then maybe this is not efficient to spend the money here. We spend it later in the renewable energy systems. And then you can get, obviously, these load profiles, but you only get the load profile for the entire city and not localized, right? Because you don't know where this load happens because you simplified it so much. You only know roughly in the program where it happens, right? But you don't know where the location is per se. So this is a part of my PhD work that I did here. I took this kind of typical room approach, but automated it in a way that you can now simulate cities building by building in an accuracy that is similar to the archetypical full-scale building energy model, but at the speed of these kind of simple typical room approaches. So what happens in this approach is we do a contextual analysis. So in radiation analysis, this could be expanded to, for example, wind exposure or pressure coefficients on the facade. You cluster it, and then you position these typical rooms in these clusters. You simulate these clusters, and then you can map this result onto these buildings and in a really fast way, right? So the typical energy model is around half an hour. This takes 1 minute to simulate. just at this kind of scale. And what we are seeing here is I think this has around 160 zones, and this is 8 zones, right? And you can get very, very similar results. So the validation of this was quite thorough, looking at different climates, different construction standards. So all these kind of very tedious changing parameters that you need to look at. And the error in the end was like around 2 to 4%, if I remember, 3%. So that's quite interesting. And then over the temporal, the resolution is also quite close, right? So the dotted line is the full multi-zone building energy model, and then the solid line is what the new kind of simplified automated approach was able to simulate. And now with this, you can do interesting things. You can kind of scale FAR and look at the daily total loads that you get, and you can see how close you are to kind of net zero carbon if you then know what your renewable energy yield is. You can do these, you can visualize the entire city and say, okay, this is a cooling dominated building, this is a heating dominated building, and you can look at the loads in great temporal detail, but also spatial detail. I think this is the biggest difference there. And the nice thing, since we have so much information about the facade clustering, you can you can even optimize or paint optimal facades onto the buildings, right, before the design even happens. So you could make in a master plan then start, regulatory recommendations or requirements that certain facades need to have either shading systems or the window-to-wall ratio can't be that big, and so forth, right? So that's quite interesting. This is all packaged in simulation software that's available to you. You can download and use it for free. This is called UMI. It's the urban modeling interface that does the urban part. ArcSim is the kind of building level simulation software. Now I also had this prepared, but I think we're getting close to the end. This is something that we are doing now for the campus. So we're basically taking these energy models or these energy modeling tools that we've developed, and we're applying them to our campus to kind of see what's happening to them. And I'm just going to skip through them quickly. What I wanted to show here is that now what we can do for these buildings, we can project into the future, right? So we have future climate files, and this is actually a graph that Thomas produced here in the back, where we look at over time, 2020, 2050, 2080, what happens to the buildings, right? So a heating-dominated building, that shrinks, or the heating demand shrinks, obviously, with global warming, and the cooling demand rises, which is good for Cornell since we have lake source cooling. That's kind of free cooling. But even for retrofitting analysis, that's interesting. So if you were to choose to kind of swap out all the windows in the older kind of art squad buildings, you would probably today go with like something like triple pane glazing if you think this is the best glass to prevent heat loss. But actually, over time, this is not the best solution, right? The best solution is the green one, which is a double pane glass with a special coating. And these are very simple analyses that we did in one semester, I believe. So you can imagine what you can do if you had these energy models for all buildings on campus. You could really kind of try to kind of inform the sustainability strategy of Cornell. Okay, so let me end it here, since I think there needs to be 5 minutes of questions. If you're interested, please reach out. We're always looking for people that work with us in the lab if these projects sound interesting to you, and I'm happy to take questions.
Okay, so this will match on a shorter report, right? Asking questions.
Yeah.
You discussed daylighting was always to the southern side, which makes sense if you're designing it that way, but would the same concepts work for a building that's already positioned to a different direction?
Yeah. So for this study, what we did is we did east-west facing also, and southern. So you need direct sunlight access. So northern facades don't work that well for this kind of approach for daylight redirection, but it does work in all kinds of orientations.
So actually, I want to ask questions.
Yeah.
For the benefit of the student, some of them may work in the in the building industry or building construction or building energy consulting. So you sort of mentioned this, right? So can you sort of give us a description of how currently building energy modeling being used in the design?
Mm.
And also, what's your vision for the future? I mean, you already sort of, it's like a totally automated process, right? But how currently being used?
I mean, current practice is that you have an energy modeler. It's a consultant that you hire at some point in the design process. And things have changed, right? So people realize that they're leaving a lot on the table if they don't do this, and if they don't do this early, right? So at the time when I started studying this, integrative design was like a catchy phrase that people tossed around, but really didn't happen, right? So what happened is there was a design process. You did the design. At the very end of the design process, you hired an energy consultant who kind of looked at the design and said, okay, swap out the windows. You need shading here. That's it, right? And that's really not talking about integrative design. It's like after the fact, after the design has happened, you do some tweaks to it so that it's not totally bad. But these changes then at the very end of the design, they cost a lot of money, right? They cost a lot of money because the building has already been spec'd this way, has been planned this way from an architectural perspective, right? And then someone comes in the end and says, I want to change this, I want to change that, right? So that you get a lot of resistance at that point in time because the changes, you have to redo everything, right? So that's really not the way it should be. And so companies like Transolar or Atelier 10 and so forth are these consultancy firms, and they've pushed into kind of earlier phases of the design where they accompany architects kind of from early design stages on and kind of consult with them and so forth. But still, there's always this back and forth and translation issues, and it's not a very effective way of kind of optimizing these things, right? You as the person controlling the design you need a fast way to do this because you can't wait for 2 weeks until the energy consultant has compiled his report, then studied the report for 2 days, right? That doesn't really work. So design decisions are made quickly, and they're made like within seconds sometimes, and you want to be able to kind of have these simulations running, giving you constant feedback without you having to kind of tinker with them all the time, right? And you want to focus on something else. You want to focus on a building that is loved by the people who are in the building. And energy is important, but it's just one parameter out of many for an architect. And there needs to be kind of this much more integrative, much more integrative workflows. I'm not saying that the engineer and the energy consultant are obsolete with the tools that we develop, right? That the tools are more like a common language that both sides can use, and then all of a sudden the collaboration works a lot better. And some of the settings that you have to do in these tools, they have to come from the engineer. But as a designer, you can test your design decisions live because you just load templates and automatically run simulations and get the feedback instantly, and no one needs to compile a report for you.
I was kind of wondering, so you talked about the two spatial looking for the sunlight.
Mm-hmm.
Are there other strategies out there when modeling how much actual sunlight you're putting into a room to save energy?
I'm not quite sure if I understand the question. Are you talking about the atrium or the daylight redirection system?
The redirection system.
The redirection
Talking about Claire.
Oh, okay. So yeah, I don't know if I can go all the way back. So you mean like other strategies to bring in daylight? Yeah, there are other strategies, right? So this is maybe helpful as a retrofitting solution where the building already exists, very deep floor plans. You could use something like that. You just install it on the inside of the facade. And again, it's a prototype. There's lots of issues with that still, right? So you'd need to do proper glare analysis that these mirrors don't kind of reflect light into the eyes of people working there. It needs to be carefully calibrated. There's a lot of kind of moving parts which can be annoying, right, if they make noise and so forth. But it's an interesting concept that you can bring in light deeper into the space and illuminate areas that had to be artificially lit. In a way, maybe this setup is maybe not the best, with the school idea where you project light through a kind of secondary space onto a facade is a little better. I don't know. these things would have to be tested in the project, right? But yes, there are many different ways to deal with these things, right?
So actually, for this one, I saw you compare in Phoenix and but in other cities. But you started this in Munich, right?
Yes.
So how well it worked?
In Munich?
Yeah.
Well, Munich is kind of this in-between climate, right? So I only showed 3 climates here. We did this for many more climates.
Oh, okay,
Munich was one of them, but I think the ones that I showed were like very clear in terms of their difference. So we have Alaska, we have Arizona, and we have New York, right? So the one is a cooling dominated climate, other one is a clear heating dominated climate, and then something in between for New York City. And very different sun angles. Anchorage has very low sun angles, even in the summer. So the system works actually much better there. Yeah.
Okay. So let's thank again for a very exciting talk by Dr. Dogan.
Thanks.
So we are sort of putting together a pretty